All right, let's do one more example. So in this example, we're going to look at two events that are related in an interesting way. So let's say that we consider the probability that it rains in Beijing on any given day in the year. And I looked this up and it's about 0.2. Okay, and then also let's consider the probability that it rains in Philly on any given day of the year. And that is 0.3. Okay, now it also turns out to be the case. The probability that it rains in Beijing and Philly is 0.06. Okay. So let's look at this and let's try to match it up with what we learned so far. So we saw that the probability of an event A given B is the joint probability of A and B both occurring over the probability of B. So let's say that A here is Beijing, or actually I'll make it Philly. A is Philly and B is Beijing, B for Beijing. Okay, so what's the probability that it rains in Philly given that it rains in Beijing? So let's just plug these numbers into the formula. So the joint probability of raining in Beijing and Philly is 0.06, and the probability of raining in Beijing is 0.2. So when I divide that out, I actually get 0.3. So interesting. What we just showed is that the probability doesn't change when we condition on Beijing. Okay, let's check the other way around. So what if I know that it's raining in Philly? What is the probability that it's raining in Beijing given that it's raining in Philly? So again, I'm just going to plug in the formula, 0.06 over 0.3. Well, that gives me 0.2, which is also the same that it rains in Beijing no matter what. So what we notice is that it doesn't matter whether one is happening or the other is happening. They don't affect each other. So the probability that it's raining in Beijing, regardless of anything else, is the same as the probability that it's raining in Beijing, given that it's raining in Philly. And the probability that it's raining in Philly, regardless of anything else, is the same as if I knew I was raining in Beijing. So raining in Beijing doesn't change the probability of it raining in Philly at all, which kind of makes sense because they're on the opposite side of the world, right? So we call these independent events. Okay, it's very important. People mix this up with disjoint, and that's not what it is at all. What it's saying is, yes, the events overlap. But if we look at the overlap and we restrict it to one of the events, it doesn't change the probability of the other event that we're looking at. So they're not disjoint, they definitely overlap, but we have this independence. So if I write the formula down, what I'm saying is the probability of A given B is equal to simply the probability of A. Another way of saying it is that the joint probability of A and B is equal to the probability of A times the probability of B. And if we look at that above, well, that's certainly true. Probability 0.2 times 0.3 is 0.06. And the reason we see that is simply by plugging this in, the fact that we already established, into our conditional probability formula. So A given B is probability of A. So you just plop that in there, multiply both sides by probability B, you get the joint probability is probability of A times probability of B. So this is what we're assuming in the Markov chains, actually. So we're assuming that it doesn't matter the characters that we've drawn before, that when I draw a character the next time, it's kind of starting fresh. So we only need to know the transition probabilities from one character to the next. We don't need to know what happened to all the characters before. So anyway, it often really simplifies our life, as we'll see more in class when we start to use this for classifiers. Okay, but that's it for now for conditional probability. So this is a very important topic. Make sure it makes sense. I'm going to have a couple quick exercises on it.